All right. Hello, everyone. Welcome back. Glad to see you all as we return to some kind of normalcy. Um, Glad to see you all are here because that means hopefully that things are somewhat stable in your life. If they're not, I apologize. Um, if any of you have been significantly affected by this whole storm thing to the extent that it's going to affect your performance in this class, reach out to me so I can work with you. I never want things outside of this class that are outside of your control to negatively affect how you all do it here. Because I get that life is more than what happens in these however many walls you count in this room. So if that's you, please reach out to me so I can work with you. But yeah, it's been a week. So I'll give you all a joke because I always forget to do that. Did you hear about the man who got cooled to absolute zero? He's okay. Yeah, it's good. Yeah. Absolute zero. It's good. It's a good science joke. All right. So, let me give you all some logistics updates. I sent out announcements. Let's talk through them. Actually, let's go to your all's web courses. This is more relevant. All right, so I sent an announcement to you all detailing how we're going to respond to this whole hurricane thing. And the long and short of it is everything is shifted back a week. That's really it. So let me kind of show you what that means in practice. So if y'all go to the simple, the home page is all the due dates. Everything is shifted by a week. Everything's been shifted by a week. If you go to the simple syllabus, you'll also see. And this is the most important thing that has changed is test 2's date. That is the one. I put it in the email. I put it in all bold, all that kind of jazz. But just to really make certain we're all aware. So everything got shifted back a week. We'll finish work in Kinetic Energy today. Today's the 15th, so by tomorrow you're good to go. So the quiz for work in Kinetic Energy will open tomorrow. If you already started it, I kind of went through and gave you, if you kind of already initiated it, I went through and I think gave people extra tips to make up for that if you kind of were proactive and already started looking at things. So tomorrow it'll open. Everyone will have the 2 attempts. It will be due a week from tomorrow, like classic quiz stuff. We finish the content. You have a week to do the quiz, and then it repeats. Great. Test 2 is on Tuesday, 11/12. Tuesday, 11/12, which here's today. So that's 1, 2, 3, 4 weeks from today is when we'll have our next test. And then after that, y'all, we only have 2 weeks of classes. That's the result of all this delays and all that. So, if you have a conflict, a known conflict with this exam, let me know sooner than later. I recognize that things have shifted. I told you all the exam dates at the very beginning of the semester. Those are no longer the same because of hurricanes. If you have planned something that conflicts with that, and you planned it well in advance, and you're being very responsible and planning it around the other testing, let me know and I will work with you. Let me know sooner than later, and I will work with you and make sure you're not penalized for, again, things outside your control. As far as we are aware, as far as anyone has told me, the final exams are the same. I have heard nothing otherwise, so our final exam date has not changed because I haven't heard anything otherwise. What I have done is the 2 weeks following the exam, we are going to cover torque and moment of inertia. I'm just not going to be able to cover as much as I would have before. So I'm just going to cut some content. I'm not going to try to cram the same amount of content in less time. That is not worthwhile. I'd rather teach a few things well than a bunch of things crappily. So, I will this has no effect on exam 2. Exam 2 is not affected in any way as far as content is concerned. But the couple weeks afterwards, we will cover quite all the things I wanted to with rotational stuff. So there'll be a little bit less in the final. Same number of questions, just not a little bit less about rotational stuff. So anyway, Problem set 3, I need to pare down. Problem set 3, I need to pare down, and I also deleted the last quiz. That was related to those things as well. So there you go. All the recitations I've gotten shifted back a week. They're mostly aligned. The recitation for this week is on work and energy, which we're finishing today. So it's not ideal. If your recitation is today, you potentially saw stuff that I haven't taught you yet. But it's mostly okay. It is what it is. It's the best I can do, right? All right. Your all's free response grades should hopefully be finished grading by the end of this week. The grader is working on those. I checked with him. So the same expectations I had for you all during the break is the same expectations I had for the grader. Specifically, I didn't expect you to focus on this class at all. During the hurricane, my expectation was you all were taking care of yourself. And the grader, I had the same expectations that they take care of themselves during the hurricane. So that's why the grading isn't done yet. So by the end of this week, hopefully, a week delayed, which it matches up. Hopefully those will all be done, and I'll upload those, and all will be well. I will go over that. Because of the hurricane, I have one last makeup. Next week, I'll go over that problem. There's one problem that I'll go with. Next week, I'll go over that one. And whatever that problem is, you can almost guarantee there'll be one like it on the final. Because it's a good problem. It needs maybe a little bit of work formatting, but it's good overall. All right. Any other questions, logistics-wise? All right. 2 cool science things that have happened. One, the Nobel Prize for Physics was awarded this last week. Nobel Prize is awarded every year. The most interesting thing about Nobel Prizes is it kind of shows what's valuable currently. So the Physics Nobel Prize, really interestingly, was about developments in AI, which, you can make arguments, is that physics, is that not physics? I guess they use physics concepts to help with the large language models. But that's interesting, right? It's an interesting kind of societal, cultural kind of thing you can look at. So anywho, the one for physics was based on AI. The one for chemistry was also based on AI, using AI for determining something. RNA, DNA, something like that. I don't remember. It's chemistry. It's not that important. No, it's important. So anywho, interesting though, always to track that. And the other thing that was kind of cool was yesterday, a rocket launched with a satellite that's called Clipper, I believe is the name of it. There's a couple really cool YouTube videos one's by Veritasium, the other's by Real Engineering. Really, really cool science, really, really cool engineering. So this satellite called Clipper, it's going to Europa. It's one of Jupiter's moons. What's really interesting about it is it's really radioactive, not because there's a bunch of uranium or stuff like that, but for other cool physics reasons. And it's just, check it out. It's cool science. The videos by Veritasium and Real Engineering are really, really good on it. And it's just cool science that's happening. What's interesting about that is it won't arrive till like 2030. It's a long way between here and there, and it costs, you could get places fast in space. Remember, there's an object in motion remains in motion, object at rest remains at rest. So if you're burning a bunch of fuel, you're accelerating constantly, you can get somewhere really quick, but fuel is expensive to get into space. It's weight, and weight costs energy. So it's just, there's a lot of interesting physics in rockets. Anyway, check it out. Highly encourage it. But it's just kind of 2 cool things that happened in the last week in the midst of a thing that wasn't that cool. Oh, yeah. That was the third one. Yeah. The SpaceX, which is insane because when I watched the video, so SpaceX, they caught a rocket the size of like a grain silo. Thing's massive, and the thing looked like it was on the verge of like not surviving. There was like fire coming out the side, and so that's stuff. Yeah. Thanks for reminding me of that. The SpaceX stuff, cool stuff that's happening in the mix of not cool stuff like Hurricane Milton. It's good to kind of notice these things. All right, so getting into, let me remind you all, it's been a week and a half. What the heck did we cover like a week and a half ago? So we talked about work and energy. And so I told you all this quote by Richard Feynman that basically said, energy is made up. It's a tool. You calculate it. Stuff happens. You calculate it again, and the numbers are the same. And that's energy. And it's a really, really useful tool. And we're going to see some uses of it today. Some problems that would otherwise be really hard to calculate. So then, great, there's energy. Then we talked about work, which is basically how much energy gets added to a system or taken from a system. And the equation for this was the integral of f dr cosine theta. So great. We looked at that. We did some problems with it. It was good stuff. We talked about what was doing the force. And there's going to be some things I'm going to reiterate. We talked about positive and negative work. Positive work is adding energy. Negative work is taking energy. You're not creating. You're not destroying. You are just adding energy to the system or taking energy from the system. Where is that energy coming from and where's it going to? Whatever's around it. Whatever's around it. So, an example is if you push a box on the floor, friction does work. It takes away energy from the system. Where does that energy go? The surface gets hot. The surface it's sliding on gets hot. It stole some energy. All right. Great things. Math. Check these things out. All right. The last thing I left you all with was something that no one liked. Like the vast majority of people weren't happy with the answer. So I gave you all two scenarios. I said, hey, I push a box and two different paths. Who did more work? And the one that took the longer path did more work for friction. And then I gave you the same problem, but instead of friction, I said for gravity. I said, hey, you got someone that goes straight down. So a car goes flying off a cliff and hits the ground, and someone else takes a windy path. Which did more work, and the work was the same. And I left you all with this. We kind of finished in the last couple minutes. And so this is conservative forces versus non-conservative forces. Conservative forces don't care about the path. That's gravity. Doesn't matter the path you take. You only care about the beginning and the end. And the reason for that is that if y'all remember the equation, work equals integral of f dot dl. Conservative forces, F, direction of F does not depend, and I'm going to make this bigger so it's easier to read, does not, oh, it's going to do that. It's so weird. Why does it do that? Somehow me touching the screen makes it very angry, so I guess I'm not going to do that anymore. All right, direction of F does not depend on dl. Does not depend on dl. All right, gravity. Gravity's always down. I don't care what path you're taking. Gravity's down. If you're traveling to the left, gravity's down. If you're traveling to the right, gravity's down. If you're traveling down, gravity's down. No matter which path you take, force of gravity is always the same. Whereas the direction of path can, vary. Non-conservative forces, direction of F depends on dl. Depends on which way you're going. Friction is always opposite the direction you're going. So if I draw a squiggly line here, if you're traveling to the right, friction is to the left. Friction is always opposite the direction of travel. If you're going down, friction is going to be up. So this is the difference between conservative forces and non-conservative forces. Conservative forces don't care about what direction you're going. So you just care about the beginning and the end of the problem. Really much simpler in calculating. Friction and forces like friction, air resistance, applied forces, depend upon the path you're traveling. So it's important because it changes how you do the math. And honestly, it matches your intuition. When you start solving problems, you won't even think about this, but these are phrases that will get tossed out at you. Conservative forces, non-conservative forces. And at the end of the day, what I just need you to know is that if you're working with gravity, you only care about where you start and end. If you care about friction, the path matters. Okay, that's the punchline there. And that's the reason for the last two questions. All right. So great, that's work. That's work. Did some problems on that. Next, if you do work over time, the amount of energy you put out per second. Oh yeah, go ahead. Sure. That's just from the integral. Yeah, dl, dr, just whatever, yeah, direction you're going, dx, dy. It's just a direction you're going. Yep, that's a good question. Yeah.
Elastic springs are the same like in space.
Ooh, yeah, elastic springs. These do not depend upon the path you're going. They're always a set direction. If you are pulled away from, it doesn't matter whether that spring's moving left or right. It always wants to move towards the equilibrium. Regardless, so, if you have a spring that's getting stretched, it doesn't matter whether that spring's going this way or this way. If it's stretched outwards, the force is inwards. Yep, in space, springs don't care about whether there's gravity around. Yeah.
Elastic, by elastic, does that mean how far the spring stretches, or does it mean that the spring is made of rubber?
That's a good question. Elastic spring is just any spring. It's a spring that snaps back to its original position. Yeah, if I just put the word spring, same thing as elastic spring, just another adjective up front means the same thing. Something that snaps back to its original position, whether or not you squish it or stretch it, doesn't matter. That's a good question. All right. So the next thing is actually very straightforward. It's a word that you all probably heard before. It's power. It's the energy output or used by an object per unit time. It's how much energy it's converted, either gaining per second or losing per second. And I say gaining or losing. It's generally getting converted from one form to another. So the unit is watts, which is probably a word you've heard before outside of physics, specifically with a light bulb. Light bulbs have watts. What does that mean? So let's, back in the day, you had incandescent light bulbs, and they were about 100 watts. A really bright incandescent light bulb was 100 watts. Nowadays, you can get a LED light bulb that's equivalent, that's like 10, 11 watts. This is literally how much energy it's converting from electricity to light/heat every second. So this watts is the exact same thing as joules per second. It is not creating energy. It is not destroying energy. A 100-watt light bulb is just converting 100 joules of electrical energy, into light and heat every second. It's changing electrical energy to heat and light. How much? That much. Every second, that's how much it's using. It's an ongoing process. If it stops, the light bulb turns off. That's the whole idea here. So whenever you see a wattage, which is very relevant for this last hurricane, if you had a generator, you have to do the math to figure out how much wattage all your various appliances use to make sure your generator can supply that energy. So for example, my generator I had, which thankfully didn't lose power, but it existed, it can output 3,750 watts. That's 3,750 joules of energy. Where's it getting that energy from? It's burning gas and converting that at a rate every second. It's converting 3,750 joules of kinetic energy to 3,750 joules of electrical energy, assuming it's not perfect, there's heat loss and all that kind of stuff. It's able to output 3,750 joules of electrical energy. Your appliances use various amounts of electrical energy. You all will eventually learn in physics 2, PIV, P equals IV, on devices. You don't need to know that for this class, but it's just especially given this hurricane, I had to calculate this. This is something I had to calculate in my house to determine how much my refrigerator uses. Your refrigerator doesn't tell you how much wattage it uses, but it does tend to tell you how much current it uses and how much voltage, and if you multiply those, it tells you the wattage. And that's really important because your generator, if you try to pull too much wattage, try to pull too much current, it will trip the breaker on your generator and it will stop. You have to go and hit the breaker.
A short circuit.
So it won't be a short circuit. It will, there's a safety measure in your thing that'll trip to prevent too much current from going through it, from breaking it. So again, you don't need to know PIV for this class, but it was very, very relevant for this last week if you lost power and had a generator. So to that end, I'm going to show you all one more thing that, again, not necessary for this class, but it's fun to know. Let me jump to it real quick, and then I'll come back. Kilowatt hours. Kilowatt hours is what you're charged for by the electrical company. So how does this work? Let's say you have a 100-watt light bulb. 100-watt light bulb, and I want to calculate how much it costs to run this light bulb. You convert it to kilowatts. Really straightforward. 100 watts is equal to 0.1 kilowatts. It's just, it's kilo divided by 1,000. Great. Let's say you use that light bulb 3 hours a day. 3 hours a day. And then your electric company, which is Duke or Orange County something, they charge you. If you all look at your electric bill, if you pay the electric bill, if you check it out, you will see that there's a cost per kilowatt hour. Why is it kilowatt hour? It's literally taking, let's remind ourselves what this is. This is 100 joules per second. If I multiply that by time, I get energy. They're charging you based on how much energy you use. If you take energy divided by time and you multiply it by time, you just get energy. That's what they're charging you for. How much energy you use. All right. I just looked at my Duke power bill today because I guess it's higher than I thought it was. The cost per kilowatt hour is about 0.13 cents, maybe about 14 cents. Check out your own electrical bill. Anyway, so if we want to calculate the cost to run a 100-watt light bulb, 3 hours, you just take 0.1, take the kilowatt hours, or the kilowatts, multiply it by the hours, multiply it by the cost for a kilowatt hour, and that comes out to a number. I don't know, it's not a super exciting number. Well, it's interesting. It's literally the cost. It's literally what comes out of your bank account when you inevitably pay them. There you go. It costs about 4 cents to run this light bulb for 3 hours a day. What's cool? A 100-watt light bulb is very inefficient. The reality is you're hopefully using LEDs. If you use an LED and you do this same math, it's really simple to do this because it's just move the decimal place. It literally costs you less than a cent. It's 10 times less the cost. 1/10 the cost. So pro tip, if you all have light bulbs in your house and they're not LEDs, you should switch them because it will save you. This is for a single day, for a single light bulb. If you kind of multiply this by how many light bulbs are in your house, and you multiply that by how many days are in a year, you can save yourself like 30, 40, 50 bucks. If you switch all your light bulbs to LEDs, and within 1 year you make back your money and then some. It's a really good investment. I mean, it's not much, but it's 10, 20 bucks more than you had every year. So there you go. I'm not going to test you all on this, but it's a good connection for power. It's something you all see every day. All right, let me give you all a problem that does involve power. And this one is it's a math problem for sure, but it's do you understand the concepts? That's how we're going to solve this. So this problem says coal is lifted out of a mine a vertical distance of 50 meters by an engine that supplies 500 watts to a conveyor belt. How many kilograms of coal per minute can be brought to the surface? Ignore the effects of friction and assume the conveyor belt moves at a constant velocity. All right. It's an interesting problem. It's a really fun, it looks worse than it is. It's a really interesting conceptual problem that when you kind of get the concepts for it, it's pretty straightforward. So let's write down our givens. I mean, I guess we could draw a picture. Coal goes up. I don't know. There's not too much. Gravity is down. We're not going to end up using this too much, but I'll make mention of it. Notice I didn't tell you whether this was a winding path. I didn't tell you whether this was straight up and down or at an angle, because gravity is a conservative force. And that's the only thing you're fighting against. You don't care about the path. So again, we get to connect back to that. All right. What did I give you all? I gave you all power, which is 500 watts. What else did I give you all? I gave you all the distance it needs to move vertically. How do we want to write that? I'm going to put it in this way. Y final is 50 meters. Y initial is 0 meters. If you want, you could call the displacement 50 meters. You know, delta y is 50 meters. There's our displacement. And yeah, that's all that's given in here. I want you all to spend some time. Think about this. Yeah. Oh, it does give... I will... Sure, we'll do step 2. We are solving for the mass... And this is kind of... We're solving for kilogram per minute, which is going to be mass per time, which is kind of weird. I'm just going to put kilogram per minute equals question mark. It's the easiest way, I think, to express it. I can't just put mass over time because the time's in minutes, and that gets kind of weird. How do I solve this? And what I encourage you all to think about, obviously it has to do with work. So I want you all to think through what work is having to be done. How much energy can I output every second? Those kind of questions are what's going to get you through this problem. I have to do a job. I have to lift some coal. How much work is required to do that? How much energy do I need to lift that coal? And then subsequently, how much energy can I output every second? And then you can kind of, using those two pieces, you can kind of logically think through this problem. So, spend some time. Think about it. It's a fun puzzle. So there's 2 things I had you all think about. First thing I said is how much work is required. Now be careful here. The unit for power is watts, which is a W, and the symbol for work is a W. Symbols and units aren't the same thing, but it's really easy to get those mixed up. It's really easy to see 500 watts and say that work equals 500. That's a really common mistake because they share the same letters. And the reminder to you all, if you're like, what's going on there? Remember, if I told you 10 M, you would not say that's 10 mass. You would say that's 10 meters. So that's kind of a touchstone for you all if you're like, what's going on here? 10 meters is a measure of X, distance. It's not a measure of mass. Just like 500 watts is not a measurement of work. So I just mentioned that because that's a classic. All right. So anyway, what are we trying to overcome here? What are we trying to actually beat to lift these things? We are overcoming gravity. And remember, gravity is a beautiful thing in that integral of F. So, you know, F dl cosine theta. The force of gravity is a constant, so we pull it out. The integral of dl is just how high I move it. How high do I move it? Delta y. What's the angle between these 2 things? Well, so here's the thing. Why am I calculating gravity? Because for this thing to move it upwards, it's got to beat gravity. Gravity is kind of taking away stuff, so I got to add stuff. This is how much I can add. So by calculating the work due to gravity, I can equate that to the work the conveyor needs to do. They're the same. The work that the conveyor needs to do is the exact same as the work due to gravity. Why is that? Constant velocity. So force applied plus negative Fg equals 0. They're equivalent to each other. Long story short, this is what I got to beat. This is what I need to beat. I need to beat gravity. I have to put, that's the amount of energy I need to lift 1 kilogram. Well, however much mass I have, this distance times this. So I can calculate the energy to move 1 kilogram. How much energy can I output? So then we look at power. Power is defined as the change in work over change in time. 500 watts. Literally, to write that another way, 500 watts is the exact same thing as 500 joules per second. So, I want you all, I'm going to copy all this over. Y'all see if you can put the puzzle pieces together. I've given you the puzzle pieces. See if y'all can figure out what to do with them now. We know what we need to, we know how much energy is necessary to move some mass. We know how much power, how much energy we can produce every second. So how much mass can I move every minute? Oh, and you know you got the right answer when you get 61.2. All right, so there's a few ways you can kind of think through this. The way I like to kind of think through this is I like to say, all right, great, I can output 500 joules in 1 second. How many joules can I output in 1 minute? I kind of like to go from that route. So for step 4, I want to say, hey, 500 joules per second. How many joules is that per minute? You just multiply it by 60. That's how much energy I can output every minute. If I can do that much in 1 second, I can do that much in 1 minute. 30,000 in 1 minute. Great. Why is this useful? So what I can now do is in 1 minute, how much can I move? So in 1 minute, I can do 30,000 joules of work. In 1 minute, I can do 30,000 joules. In 1 minute. Great. What's the point of that? Set that equal to mg delta y. That will literally tell me how much mass I can move in 1 minute. So this is, again, it's more of a concept problem. It's kind of a puzzle. It's kind of a logic puzzle, the way I approach this problem. A little bit less, I mean, we're using formulas and things like that, but it's really, do you understand what power is? Do you understand what work is? Do you understand to lift this thing? You got to overcome gravity. That's kind of what I'm using here. So 30,000 equals however much mass I can move times 9.8 times 50. And you do the math and you'll get that the mass per minute equals that. Yeah. Oh yes, that's a great question. Very, very good question. If it's on an inclined plane, do I have to break it apart? And the beautiful thing about this, remember gravity is a conservative force. So we don't care. Yep, we don't care about the path that we have to take. Because if it's a conveyor belt, we're not considering friction here. We're not considering, who cares if you have to take a long and winding path? We're ignoring friction. So you just got to beat gravity. Gravity is the only thing you got to beat. And if it's a really low angle, then for every distance it travels, it doesn't have to work that hard, but it does over a longer distance. So the effects cancel out. It's a great question. The path doesn't matter.
Easily converts the 30,000 joules to 30 kilojoules.
If you did kilojoules, the challenge is, so you got to keep things in base units. You got to keep things in base units. So I kept this in a base unit. I just found how much energy I could output in 1 minute. That's what I did here. By multiplying this by, in fact, let me even change this. There we go. I got rid of it, so I converted power into energy in that 1 minute. And I did that using this equation. Yeah, it is 30 kilojoules.
If you were finding
you want to leave things. The only time we do so the kilowatts that we mentioned before, that's only in calculating the cost. Yeah. Otherwise, the only unit that gets kilo is mass. All right. So spend some time on this. It's a fun problem to work through. It looks more complicated than it is when you look at it from first glance. Reminder to you all, definitely try this out. It's a great conceptual question. Even though it's a mathematical question, it's a conceptual question. Do you understand the relationship between power and work? Do you understand what you have to beat to lift something upwards? Work due to that. All right. Not going to bother with this one. We're going to get to the last part. This part, we are now past, in my opinion, the conceptually tricky stuff. Moving forward for this week and next week, energy, it's all going to be fairly straightforward. Conservation of energy, kinetic energy, potential energy. But what will continue to persist, what you all do need to keep track of, work is how much energy is added to a system or taken from a system. You need to remember that throughout all this energy stuff. Work is how much energy is added to a system or taken from a system. Positive work, you add energy. Negative work, you take away energy. And there's a couple bullet points or a couple slides here I'm going to have at some point that just remind you all throughout this of like, hey, you got to keep these things in mind. Scalars, vectors, all that jazz. We'll get to those. All right, great. Here's a question that you probably were able to answer in middle school. How does an object gain kinetic energy? Half of what I'm going to teach you today is something you probably knew beforehand. The other half is making it, we'll call it college level. I don't know. This is very odd. Is it not working? Is it working? I haven't gotten a single response to this physical one, which is weird. No response. All right, something's weird here. I'm going to redo this problem, y'all, because it says 0 responses. I have no idea why that is. So I'm just going to reset everything. Always the classic, right? All right. Hey, look at that. The power of restarting it. All right, I'm going to give you all to 30 seconds for this. Don't overthink it. This is not a trick question. Five, 4, 3, 2, 1. All right, this is just a definition. Not much to say about this. We're going to discover it, but hopefully this is just to show, hey, you've seen the word kinetic energy before. Kinetic is motion. The faster you go, the more kinetic energy you have. Great. I'm going to teach you all where the equation for it. You've also probably heard the equation for kinetic energy, 1/2 mv squared. We're going to derive that equation. It didn't just come out of nowhere. It wasn't just written on a wall in a cave somewhere and someone found it and said, oh, that's kinetic energy. And we're going to derive it using stuff you know. So I have this beautiful derivation, like this step-by-step. It is written out here because it uses some tricks that I would forget, so it's in writing so I don't forget. But the logic is so simple. It's great. It's super, super nice. All right, work equals the integral of force times distance. Great, that's the definition of work I gave you all last week, so that's where we're starting. What do? Well, F equals ma. We learned that before, so we make that substitution. We then make the substitution that A equals dv dt. Hey, we learned that before in kinematics. So we make that substitution. Then we do a little trick where we just multiply by 1, i.e. we put dx over dx. Seems a little silly, but trust me, it's useful. You're allowed to multiply things by 1. Changes nothing. Dx over dx is 1. So great, we put that there. On to the next slide. So great, we got our dx. So to help you keep track, we had the force, then the A, then a random dx dx. We just do a little swap. It's multiplication. We're allowed to swap things. Swap the dv and the dx. 2 times 3 is the same as 3 times 2. Nothing stopping us from swapping those things. It's just multiplication. You can swap multiplication. So great, they swap locations. Now the dx is on the left and the dv is on the right. They swap spots. Okay, cool. Why did we do that? I can't erase anything anymore. Whoa. All right. Is it angry with me? Great. All is well. Okay, why do we do that? Now, we cancel things. There's a dx here and there's a dx here. Get rid of them. Ta-da, we canceled them out. So now we're just left with dx dt and dv. Just cancel stuff out. Every single step here is a very simple step. It's just a bunch of simple steps together with logic, with like equations we've learned before. All right, what's the point of that? Dx dt is v. That's the definition of velocity that we learned before in kinematics. Great, what's the end result? This integral. The end result of all of this work is that the integral of f dx is that. All right, great. So what? Go ahead and integrate it. What is the integral of mv dv from initial velocity and final velocity? Initial velocity is va, final velocity is vb. All right, we'll go for like 10 more seconds. And 5, 4, 3, 2, 1. All right, so fairly straightforward integral. VA, VB, MV dV. Mass is a constant. We're going to assume mass does not depend upon the velocity. Now, you could have some crazy examples where it does, like a rocket where it's fuel when it leaves as a function of how fast the rocket's going. So, but it is important to think about those things. All right, great. So mass gets pulled out to the front. Woohoo. The integral of V is just, so you get m v squared over 2 with my boundaries being these, and you plug them in, and you get the second answer. There you go. So what's cool about this, you all just derived kinetic energy. You just derived, this is where the 1/2 mv squared comes from. An equation you probably have seen at some point. If you haven't, don't worry about it. But if you have, it didn't just come out of nowhere. This is what's cool about, so in physics classes, everything you learn either comes from an observation of reality. F equals mn. That's an observation of reality measurement. The relationship between position, velocity, acceleration, observation of reality kind of stuff. Everything after that is all built on that. Everything builds on it. I will never give you an equation that just like, I just say, this just is what it is. It is either an observation from reality or it's built from observation of reality. Now, your all's engineering courses in the future, they will 100% give you equations and just say, just trust me. Because the reality is, some of the equations you are going to work with, to understand where they came from, you need to do like 10 years of schooling. And so it's unrealistic to expect you all to do that. But if you're a physics major, we don't get to like as complicated equations. But we understand everything you learn as a physics major is built on something else you've learned. And so that's the cool thing with this stuff. It's not out of thin air, y'all. There's a reason, and there's reasons you can understand where these came from. Any equation I give you all in this class can come from something you can either measure yourself or derive yourself. We're not doing any crazy nonsense in here. So that's why this is just kind of cool. So there you go. There's kinetic energy. There's the equation for it, 1/2 mv squared. We're going to come back to that whole minus stuff in a second. But for now, kinetic energy is 1 half mv squared. It is a measure of the energy associated with the moving object. And again, this comes from that work equation. Every type of, so kinetic energy, potential energy, spring energy, all of them are going to come from the work equation. They're all going to get derived from that equation. Eventually, we'll learn next week, this week, depending on your frame of reference. Potential energy is mgh, comes from the work equation. The energy stored in a spring, 1 half kx squared. It's going to come from the work equation. They all come from that equation. How much energy is added or taken from a system? Yeah, and you might see things, so you might see kinetic energy as K, you might see it as KE. I don't think there's, I guess you can put an E with a lower K next to it. I don't know. There's often a few ways people write kinetic energy. But it's an equation, very simple, very straightforward. And let's do a quick practice one on it. This next question is to prove something. It's not a trick question. What has more kinetic energy? A 1,000 kilogram car going 30 meters per second, or a 2,000 kilogram truck going 15 meters per second? You can brute force this problem. Literally just plug in the numbers, compare them. Or you can recognize that the mass of the car is half the mass of the truck, but the velocity of the car is twice the velocity of the truck. And you can use that logic to using the equation. It's not a trick question though. Think through it. Do the math if you want to be careful. But these ratios were chosen on purpose to prove a point. I highly recommend do the math to double check whatever logic you might reach. The math takes you 30 seconds. Because currently half the people in this class are wrong. Do the brute force problem solving. Don't overthink it. All right, we'll go for like 10 more seconds. We'll close this out in 5, 4, 3, 2, 1. All right, so you can brute force solve this, y'all. Literally just plug in, if you want the kinetic energy of the car, 1/2 times 1,000 times 30 squared. And then you do that for the truck and you compare the numbers. But I'm going to show you all how to compare them because the next problem I'm going to give you is a ratio problem. So in the next problem, I won't give you numbers. I'll say, hey, I changed this. What happens to the kinetic energy? So let me show you all how to do this. So here's the kinetic energy of the car. K1 equals 1/2 M1 times V1 squared. Here's the kinetic energy of the truck. 1/2 times M2 times V2 squared. Why am I doing this? I'm just going to do everything in variables to prove a point here. If you can figure out these ratios, it lets you think through things quicker. What I am now going to do is make these substitutions. So making these substitutions, it's 1/2 times 1/2 M2 times 2V2 squared. You got to put parentheses around it. Whatever happens to the velocity, you got to square it. So pull all those numbers to the front. So we're going to leave the 1/2 M2 V2 squared. 1/2 gets pulled to the front. 2 squared gets pulled to the front. So that gives you 4. So what do we end up finding? We find that the kinetic energy of the car is 2 times 1/2 m2 v2 squared. Oh, look, that and that are the same thing. That's how you can kind of approach these problems, these ratio. So you're going to see that literally on the next slide is going to be another clicker question with this. Long story short, K1 is 2 times K2. That's the truck. The car has twice the kinetic energy of the truck. So the purpose of this problem was twofold. One, great kinetic energy equation. The second purpose of it was to show you that velocity matters more than mass. Whatever happens to the velocity matters more because it's squared. So when you're talking about kinetic energy, the velocity is the thing that matters the most as far as how much kinetic energy something has. Yes, mass matters, it's in the equation, but the velocity gets squared. So if I make something have 10 times the velocity, it has 100 times the kinetic energy. That's a lot. Whereas if I make it have 10 times the mass, it's only 10 times the kinetic energy. 100 times is way bigger than 10 times. So, there you go. Ratio problems are really, really good. If this changes, what happens to this? If I half this and double this, what happens? And they're so good. Here's one to try on your own. What happens to the kinetic energy if I half an object's velocity? Does my kinetic energy double? Does it become 2 times the original? Does it become 4 times the original? Does it become 1/2 the original? Or does it become 1/4 the original? So I'm just writing out the same. This is how you write these out. You write the ratio. You write it in terms of the variable we care about. We said what happens to kinetic energy. So you write out both of them. So you know what your base is and you know what your new one is, and then you substitute things in. Oh, there's one more ratio I forgot to put here. The masses are the same. Doesn't say otherwise. Safe assumption. All right, give you all 10 more seconds. Maybe a little more. All right, we'll close this out in 5, 4, 3, 2, 1. All right, so notice all these are K1 equals a number times K0. So we're going to want to work with this guy. We're going to want to replace things. So 1/2, M1 is the same as M0, so that just goes there. V1 is 1/2 V0 squared. Fantastic. We pull that out. 1/2 squared is 1/4. And maybe I'll write a little bit more here. Just 1/2 times M0 times 1/4. Times 1/4 times V0 squared. Pull the 1/4. Do not combine that 1/4 with the 1/2. Do not combine that 1/4 with the 1/2. Why? Let's go ahead and accidentally do that. It's not, I can't compare that. I can't compare this 1/8 M0. So let me show you the right way. This is bad. Pull the 1/4 out. And then this and this are the same thing. Therefore, the answer is 1/4. Again, you probably could have figured that out without going through all these steps, but I can make this problem much more unpleasant. I could say the mass the mass becomes 5/7 the other one, and the velocity becomes 3/10 the other one. And doing that in your head would probably not be as pleasant. Whereas if you write it out, you just write it there, pull all the nonsense to the front, and it works. So these numbers you could probably have figured out in your head, but it's really easy to make a problem that you couldn't figure out in your head. Anyway, so doing the process, it's good to know how to do that. All right, great. Fantastic. Velocity matters the most. It gets squared. Woohoo. All right. Work kinetic energy theorem. This is what you all derived. Let me just jump back. You all derived this. That's what we did here. We found that the work equaled this. 1/2 mv final minus 1/2 mv initial. That's what we derived before. And this is very important, and I should have had this here, but I didn't. Let me fix this a tiny bit. It's not the worst thing in the world, but it could be more clear. What's very, very important here, the net work. The net work. All the works together equal this. All the energy that's added and taken away from the system equals the change in kinetic energy. Okay? That's going to come into play in the problems that we do ahead. The net work equals the change in kinetic energy. And we just got a couple problems to practice this. And this is a very, very powerful tool that lets us calculate problems that you could not do with kinematics or forces. And literally the next two problems I'm going to give you are to prove that to you. Very simple tool to use, very straightforward. The math isn't bad, it's all scalars. But it lets us find out things that otherwise would be very kind of tricky to figure out. All right, so to that end, a couple reminders to y'all. Scalars versus vectors. Vectors, the positives and negatives come from the picture. Up is positive, down is negative, left is negative, right is positive. Positive and negatives come from the pictures, and you put the positive and negatives based on the direction. Scalars, do not put any positives and negatives based on direction in these problems. Energy is a scalar. Positives and negatives come from the math. Positives and negatives come from the math. So a really easy example of that is that work equation that we've been using this entire time. If you have a constant force, this is the equation. Notice it's the magnitude of F. It's the magnitude of the distance. The angle tells you whether it's positive or negative. For example, if my force is to the right and my displacement is to the left, then theta is going to be 180. Cosine of 180. Work is going to be negative. Cosine of 180 is -1. If the force and the displacement are the same direction, then the work is going to be a positive number. Now, I guess granted, you kind of have to look at the picture to see the angle, but you don't plug in a positive or negative. You don't look at the picture and say, oh, they're to the right, it's positive. You look at the picture, you find the angle, you plug it in. You plug it in, and cosine of 180 is negative. Cosine of 0 is positive. The reason I'm stressing this so much, do not plug in G as -9.8 when you are solving these problems. Do not plug in G as -9.8. And this is always the classic question. Is it positive? Is it negative? Here's the rules for figuring this out. This is why I'm putting this. This is why I'm stressing this, because positives and negatives are a classic challenge, and you can almost guarantee you I will ask you a problem on the test that says, hey, a box gets, it won't be this problem, but let's just say a box gets pushed to the right. What's the sign of work done by friction? And you have to think through it. It gets pushed to the right. Friction is opposite. Friction always does negative work. So, I need you all to understand whether or not you're gaining energy or losing energy. That's what positive and negative work are doing. All right, let's do it. There you go. It's more the same. If they're lined up, it's the same thing I just wrote down, just in typed. Parallel, positive work. Anti-parallel, negative work. And, in between. All right. Problem time. These ones, for the sake of time, I'm just going to kind of solve through. So when released, a 100 gram block slides down the path shown below, reaching the bottom with a speed of 4 meters per second. How much work does the force of friction do? I.e., how much energy is lost to friction? The environment. The surface gets hot because some of the energy is lost to it. How much? If friction did not exist in this problem, the block would be going faster than 4 at the bottom. But friction exists. So, we write our mass. 0.1 kilograms. Always convert immediately. If you ever see the word grams, that should be like a trigger for you that you need to convert. If you ever see centimeters, that's like a trigger. Milli, trigger. All right, great. We got that. We know our initial velocity is 0 because it's released, which means it wasn't moving. We know our final velocity is 4. And we know that the change in y, let's do it this way. Y initial is 2 meters. Y final is 0 meters. Just writing down all the givens. Something you can do before I taught you anything about this. Writing these givens is there's nothing new yet. Just how we're going to use them, that's new. All right, step 2. What are we solving for? The work done by friction. And then how do we solve this? Well, the key to that's in the title. Work and kinetic energy. If you all ever see anything with work and you see velocity involved, you can almost guarantee you're going to be using this. If you see the words work and you see velocities, pretty good indication you're going to use the relationship between work and kinetic energy. So that relationship is work net. Work net equals change in kinetic energy. Work net is all the things doing work on this object. So I'm going to give you all a few seconds. What's doing work on this object? Think about it. See if you can figure it out. Don't forget about gravity, y'all. Friction is not the only thing doing work on this problem. If you write the following, work of friction equals change in kinetic energy, that's wrong. Why is that wrong? Because friction, that would mean that friction results in it. What this equation says is the energy I add or take away from the system changes basically how fast I'm going. There is more than just friction in this problem causing it to change its velocity. Gravity is doing work. Now, you got to think through the logic. Is it positive or is it negative? We'll get there. So work due to gravity plus the work due to friction equals the change in kinetic energy. I am not putting any positives or negatives here. The math will tell me. The math will tell me the positives or negatives. Do not put, it's going down, so the work due to gravity is negative. Don't put that. It's friction, so the work due to it is negative. Don't put that. We're solving for it. Let the math reveal it all to you. These are not vectors. They're scalars. We do not put positives and negatives. The math tells us. Unlike vectors where we had to put it. All right, great. Work due to gravity. What is that? Well, integral of f dl cosine theta, which we have hopefully, at this point, we've seen that force of gravity is a constant. You pull it out. So the work due to gravity is the force of gravity times how far I moved, magnitude, times cosine of theta. Fg, always going to be positive here. It's magnitude. Change in y, always going to be positive. It's magnitude. It's all about the angle, y'all. So, gravity is down. Which way am I moving? Down. What's the angle between those? 0. Remember, gravity doesn't care about the path. Gravity does not care about the path. Remember the car going off the cliff or the car going down the windy path? Who cares that it's a bumpy journey? Gravity only cares about the displacement. The beginning and the end. It started at the top, it ended at the bottom. All right, so fantastic. We take all this stuff. We put it over here. Put my picture back because that is useful. Oh, and something I want to note. I saw it was on the free response. So I graded some free response for my other class and actually some for this class as well. They're not done. Just reminded you, I'll be done by this week. It was not super common for me to see people make these lists, and the result was it was harder to get partial credit for steps 1, 2, and 3. So just keep that in mind on the test. If partial credit, if you all write everything I wrote here, and this is the problem I gave you, this is 8 out of 10 points right now. If you did all these steps correctly, this is 8 out of 10 points. This is all the physics. After this, we're just going to do a bunch of math. That's the last 2 points of the problem. This is what I give the vast majority of points to. So, anywho, step 4, let's do it. So this will be mg times delta y, cosine of 0 is 1. So let's plug that in. So mg delta y plus force due to friction equals 1/2 mass velocity final squared minus 1/2 mass velocity initial squared. That term goes away because the initial velocity is 0. Plug in a bunch of numbers. 0.1 times positive 9.8 times positive 2 plus the force of friction equals 1/2 times 0.1 times 4 squared. And it's just math. You plug in the numbers and you get the answer. Oh, and I made a big mistake here. I am not finding the force due to friction. That is actually that would be much more complex to find. The force due to friction, you need to know the path. But I can find the energy lost by friction. How much energy got lost to the environment just by doing this? Who cares the path it took? All I care about is the initial velocity and the final velocity. That's all, and how high up I started. That's all you need to know for this problem to find the energy lost by friction. Really, really useful to know that. So, and you know what's cool with all this? The answer makes sense. Negative. I didn't need to do any. The math tells me that the work due to friction is negative. Friction lost and it caused the thing to lose energy. Yeah. Sure. Yeah. So step 3, all I did was I took this equation and I put it here and I took this. Yeah. It's a great question. So this is this. Yep. And so I just plugged it in there. That's a good point. Mm-hmm. Yep. And solving for the work due to friction. That's what the problem was asking for. Yeah. So why do we or why don't we? Yeah, great question. The question was, why don't we split gravity into X and Y components? The reason being, when we care about the work due to gravity, we don't actually care about, we're not having to bother with vectors. We only care about the part of gravity that lines up with the part going down, and so that cosine does that for us. Yeah, so long story short, when we're talking about gravity and the work done by it, you don't care about the path at all because it's all scalars. Yeah, it's not vectors. It's actually much easier to work with. Way easier. All you do is, gravity is super nice. At friction, you do care about the path and stuff like that, but not in this case. Okay, one last problem, y'all, and it does boil down to just the net work equals change in kinetic energy. Yep.
When you're writing gravity, it's positive. You write it as positive.
Yep. Yeah, the question is, when we write gravity, what is positive? Yes, because it's the magnitude of Fg. So here we have the magnitude of Fg. So if you want, you could put it as negative, but you better have absolute value signs around the whole thing, which gets rid of your negative anyway. Yep. When we work with energy, everything goes in as positive. How do you decide whether it's negative? Cosine of the angle. Cosine of the angle is what ultimately determines whether things are positive and negative. And all that is telling you, is it adding energy or taking away energy? Gravity is adding energy to the system. It's making it go fast. Friction is negative. It's taking away energy from the system. It's slowing it down. That's the logic that's happening here. And the math does all the work for you, which is nice. All right, so last little bit, y'all. Forces to remember. Fg equals mg. Force of spring equals kx. We are going to use that in the next problem, in fact. Springs cause forces, and force due to friction, mu Fn, we use that one so much. Very likely remember that. This next problem, we're going to need a couple of these. And the next problem, we're going to find the energy stored in a spring. Even though I haven't taught you the equation for it, you're going to derive it for yourself. Kind of, sort of. We're tight on time. I might end up still doing it, but all right, we'll at least get this next problem set up. I might not go through all the actual plugged in numbers. I will definitely do steps 1, 2, and 3. All right. A 3 kilogram block is pushed against a massless spring with a force constant of 4.5 times 10 to the 3 newtons per meters. When the spring is compressed 8 centimeters. Centimeters, immediately that should trigger you that you got to convert that. Block is released and it slides 2 meters from the point at which it's released across a horizontal surface before friction stops it. What is the coefficient of kinetic friction between the block and the surface? So let's draw a pretty picture. You got a wall, you got a surface, you got a spring. The spring is compressed. So the spring, if it was happy, it would be over there. So that's 8e to the minus 2 meters. It's squished. Otherwise, nothing happens in this problem. The spring is the thing that pushes it. Great. It does that. And then at some later point, the block is now 2 meters away. And it stops. So we just write all our givens. We got a mass of 3 kilograms. We have, and I'm going to give you all a few seconds to think about this. What is the variable for the force constant of a spring? What letter does that go with? It goes with K. If you don't know what letters go with which variables, that ends up hurting you when you're trying to find the right equation. All right. I have a little bit of a conundrum. I say conundrum. I have 2 things measuring distance. I have how much it gets compressed, and I have how much it moves. Those are both x variables, so this is where the subscripts matters. So here I'm going to put x compressed, x comp equals 8e to the minus 2. And then I'm going to put x initial equals 0 meters, x final. You know what? Let's just do this. Delta x equals 2 meters. I have 2 different x's. I put a little adjective as a subscript so we know what it is. If you put them both as x, you're going to get mixed up at some point. All right, woohoo. I think that's it here. Step 2. What am I solving for? Give you all a few seconds. What the heck am I solving for? Yeah, what's the variable for that? That's mu, mu, Greek letter. All right, how do I solve this? Well, again, we have stuff, and this is a little trickier to see because at no point does it mention the word work. At no point does it mention the word velocity. So this problem, I'm just going to tell you all, and this is one where you have to get more familiar with these kind of problems. This is, you could probably guess it because it's in these PowerPoints. Work net equals the change in kinetic energy. We're going to use that. What's doing work on my system? The spring and friction. So the spring and friction are doing work on it. Equals a change in kinetic energy. And you're like, wait, we don't know the velocities. We do. I just didn't write them in step 1. We found that we're like, hey, maybe we'll try this out. We do know the velocities. Initial velocity equals final velocity equals 0. Why do we know that? It gets pushed against a spring. It's not going to be moving. At the end, it says it stops. So, basically, if you all see problems with springs and motion and friction and all these things together, energy is probably what you're going to use. If you all see a lot of things kind of together, energy is a fantastic way. If you can use energy to solve a problem, you basically should always try to use energy because it's so much easier than forces. It's so much easier to work with than forces. Case in point, what does this problem end up turning into? So, copying all this stuff over. What's the end result of this problem? All right. These terms go to 0. So work of spring plus the work of friction equals 0. So they equal each other. One's negative, one's positive. The math will figure that out for us. Now, we got to do a couple things here. We got to actually replace these. I need mu. So let's go ahead and kind of think through. Work due to spring. How do I get that? It's the integral of F times dl times cosine theta. What is the force due to a spring? It's kx. What direction does my thing move? Instead of L, dx. And then how do you decide the angle? Which way is the force acting? Which way is the thing moving? The spring pushes to the right. Which way does it move? To the right. So the angle is going to be 0. Force of spring dx. So that's going to be 0. You have to integrate this, y'all. Kx dx. You got to actually integrate it. It's a very simple integral. It's 1/2 kx squared. It's just like you all actually kind of did this integral earlier. Integral of mv dv. Great. There you go. There's the work done by the spring. 1/2 kx squared. What's the work done by friction? Really straightforward as well. This thing's on a flat surface. So it's going to be the force times this. It's a constant force times cosine of the angle. What is the force? Mu Fn times how far it moves, which is delta x. At this point, you plug stuff in and you... Oh, one last thing. What's the angle? The force due to friction is this way. Delta x is that way. It's 180. Friction is always negative, y'all. It's always going to be 180 for friction. Why does that matter? It makes it negative so that they can actually equal each other. So using these powers combined, long story short, 1/2 kx squared minus mu Fn in this case will be Fg, and you do if you solve it. Anywho, this problem might look, I went through it quickly, so it probably looks way worse than it is. Let me rephrase that. It definitely looks probably worse than it is. Try it out, y'all. It is just a work that equals change in kinetic energy. Once you understand work, these problems are easy. Work is the hard part of these. This is really straightforward, the work that equals change in kinetic energy. Have fun. Try it out. Next class, conservation of energy.
I was saying a question that's not really related to this.
Sure, what's up?
You know what absolute is?
What?